So our linear algebraic questions in Hilbert spaces have led us to minimization problem. Questions about finding a point in a Hilbert space or a subset of a Hilbert space that minimizes a certain functional. Now we're going to start this investigation with theorem 2.1, which is the quintessential example of a minimization problem that we can have a solution for in a Hilbert space, and that's the existence of a projection onto closed non-empty convex subset. So this is literally what the theorem is saying. If I have a closed non-empty convex subset here, then I can, given any point in my Hilbert space, find a unique element in K that realizes the distance between F and K. So find a U that minimizes the distance between F and U over all possible choices in K. And in the spatial case where my convex subset is actually a subspace, then what we're going to get is a linear projection onto a subspace. So in Hilbert spaces, we will always be able to project down onto closed subspaces. And interestingly enough, there would be a characterization of the solution of that problem that's of the flavor of the type of statements we see in the Lax-Milgram theorem, for instance. And that's a characterization in terms of inner product here that tells us that U is going to be a unique element such that the inner product of F minus U is V minus U is non-positive for every V in K. So let us start by proving the theorem. So we have three things to prove here. Actually four. We need to prove the existence of the projection onto the convex set. We need to prove that it's unique. We need to prove that it's characterized by the inner product inequality. And we need to prove that in the spatial case of a subspace, then the projection is linear. Right, so these are the four things we need to do. Let's start with the first one, existence. So we have that, let's give ourselves an F in H. The distance between F and K is this infimum of V F minus V, by definition, of V in K. So we can get that as a limit of a sequence of F of norms of F minus Vn for a certain choice of Vn, for some Vn in K. So let's give ourselves a little bit of notation. Let's call D the distance between F and K, and then let's call Dn the norm of F minus Vn for all n. Right, so what am I trying to prove? I'm going to try and show that Vn is a Cauchy sequence. If it's a Cauchy sequence, because I'm in a Hilbert space, it's going to be convergent, and because K is a closed subset, the limit of the Vn is going to be in K, and that's going to be exactly the projection I'm looking for. So that's a fairly common way of proving existence, by constructing an approximation of the object we're interested in and proving that this approximation converges. Right, so how are we going to go about doing this? I'm going to look at 2 times dn squared plus 2 times dm squared. Now, right, dn is norm of F minus Vn, dm is norm of F minus Vm. So if I use the parallelogram identity, classical result from Hilbert space theory, if you can't remember it, just reprove it, expanding all the norms using inner product. This is going to be equal to the difference F minus Vn minus F minus Vm, which is great because that's exactly Vm minus Vn, norm of that, which is the quantity that I want to show gets small as n and m go to infinity. And I want to show that Vn is a Cauchy sequence, plus the sum of the two, which is 2f minus Vn plus Vm. Now, that's where I want to use convexity. Right? I look at Vn plus Vm. That's not necessarily an element of K, because K is not necessarily a subspace. But if I divide it by 2, So if I factor out the 2 here, then Vn plus Vm divided by 2 will be an element of K by convexity. So really I should divide this entire thing by 4 and get that 1/2 of dn squared plus dm squared is equal to 1/4 of Vn minus Vm squared, which is what I'm interested in, plus f minus Vn plus Vm over 2. And now the point is that because this is in K by convexity, then what I have on the right hand side has to be greater than 1/4 of Vn minus Vm squared plus d squared, right? Because the distance between f and k is a infimum. So if I look at a particular point in K being this, then I get something that has to be greater than the infimum. And now, what does that tell me about the quantity I care about, Vn minus Vm squared? This tells me that this has to be smaller than 2 times dn squared plus dm squared minus 4d squared. But dn goes to d, dm goes to d, so this whole thing, if you send n and m to infinity, goes to 0. Now that is exactly telling me that Vn is a Cauchy sequence and hence convergent. Let's call u its limit. Then we have that u belongs to k since k is closed. And that concludes the proof of the existence. Right? We have found a projection. We still need to show it's unique. We need to show it's characterized in the appropriate way. And we'll need to show that the map that sends f to u, the actual projection, happens to be linear if K is a subspace. Okay, now that we have existence, we should be proving uniqueness, but we're actually going to prove the characterization using the inner product first, because it will make the proof of uniqueness simpler. So let's do characterization. So there's two sides to that characterization. We need to prove the inner product property given that u is such that f minus u is equal to the infimum of the f minus v for all v in k. So let u in k such that we have that, and then we'll show what do we need to show. We need to show that for every w in k, f minus u inner product with w minus u is less or equal to 0. Okay, and then we'll have to go the other way and show that the unique u satisfying this inequality is the u that realizes the distance between f and k. But let's go this direction first. So, okay, let's give ourselves an omega in k, and we need to prove the inequality. What we have is that for every t in 0, 1, if I take a linear combination between u and w, so if I do tw plus 1 minus tu, let's call that v, that's going to have to be an element of k by convexity. Okay, so this tells me something, because u gives you the infimum of the distance between f and v over all v in k. So in particular for that v, f minus u, let's square that, will have to be smaller or equal to f minus v. But what is v? I mean, v is t omega plus 1 minus t u. Okay, so you can rewrite that as f minus u plus t times u minus w. Okay, and now you can expand that norm, so an inner product, and you're going to get f minus u squared, which is what we also have on the left hand side conveniently, plus t squared times u minus w squared, whatever this may be, plus 2t times the inner product of f minus u with u minus w, which is exactly the quantity we are interested in, or minus the quantity we are interested in. So now if I reorganize this inequality, I get that 2t times f minus u inner product with w minus u has to be smaller than t squared times u minus w squared. And now this is true for all t in 0, 1, and you can divide by t on both sides and then send t to 0. So as you take the limit in this inequality as t is to 0, you get that f minus u inner product with w minus u has to be less or equal to 0. So what have we proven? We've proven that if u is defined such that it realizes the distance between f and k, then it satisfies the inequality f minus u inner product with w minus u being less or equal to 0 for all w in k. Now let's go the other way and assume that u in k is such that f minus u inner product with w minus u is less or equal than 0 for every w in k. Now what can I say about f minus w squared? I can say that it's f minus u plus u minus w squared. I can expand again this norm squared and get f minus u squared plus u minus w squared plus 2 f minus u inner product with u minus w. So now if I know that this inner product here is, well, this is minus the inner product I've got there, so it has to be greater or equal to 0. So this entire thing has to be greater or equal than f minus u squared plus something, which may or may not be 0, but this something, but this whole thing is greater or equal than f minus u squared. Right. And that is true for every element w in k. Therefore, f minus u has to be the smallest possible value of f minus v to the infimum, which actually is the minimum in that case, f minus v for v in k. And that completes the proof of the characterization of the projection onto the convex set in terms of these families of inequalities that we have here. As promised, now that we have these families of inequalities characterizing the minimizer, characterizing the projection onto the convex set, proving that this projection is unique will be easy. So here is how we do uniqueness. Well, as always in a proof of uniqueness, you assume that you have two elements, let's call them u1 and u2, that are doing what you want them to do. So they are such that f minus u1, w minus u1 is less or equal than 0 for all w in k, and in the meantime, f minus u2, omega minus u2 is less or equal than 0 for all w in k. Now, if these two things hold at once, I could choose w equal u1 in the first inequality and w equal u2, u2 in the first inequality, u1 in the second. Now that would give me that f minus u1 u2 minus u1 is less or equal than 0, and that would give me that f minus u2, u1 minus u2, let's multiply all of that by minus 1, such that we have it in the same order as the first inequality. This one would have to be greater or equal to 0. But if that's the case, we can subtract the two things, and by subtracting the two inequalities, we get that u2 minus u1, comma, so I take something negative and I subtract from it, or I add to it another negative thing. It's maybe a simpler way of saying that. This will stay negative. But what is that? It is exactly the norm of u2 minus u1 squared. And the only way that this is less or equal than 0 is if u2 is equal to u1. And that completes the proof of uniqueness. So we have one more thing to prove. We need to show that if K is a subspace, then the projection onto K is a linear map. So how do we do this? Okay, we have a projection and that's what we've defined. That's what we've proven earlier. So we give ourselves to f and g in H and a scalar, lambda in R. Let's make it non-zero for that to be non-trivial. And we have that f minus the projection of f inner product with v minus projection of f. Now that has to be less or equal than 0 for every v in K. That was the characterization of what this projection is. In the same way we have that for G. And because K is a subspace, if I multiply V by 1 upon lambda, then I stay in V. So I have that F minus PKF inner product with 1 upon lambda V minus PKF has to be less or equal than 0. And then I can multiply on both part of my inner product by lambda, and I will get that lambda f minus PKF, minus lambda PKF, sorry, inner product with V minus lambda PKF is also less or equal than 0. If my lambda was negative, when you multiply the left-hand side, you change the direction of the inequality, but then you multiply again and change the direction of the inequality again. Now, what is that telling me? Well, it's telling me that lambda PKF does the job of PK of lambda f, right? Because this family of inequality characterize the projection. So I have this property, lambda PKF is PK of lambda f, which is part of being linear. Now I also need to prove that PK of f plus g is PK of f plus PK of g. And in order to do that, I'm going to modify these two statements a little bit using the fact that v plus or minus pkg is going to be in K for all v in K. That's because, again, K is a subspace, sorry, since K is a subspace. So I have that f minus pkf inner product with v minus pkf plus pkg is going to be less or equal than 0 for all v in K. And I also have that g minus pkg inner product with v minus pkf plus pkg G is less or equal than 0 for V in K. This time I subtract PKF from V and I stay in K because K is a subspace. So now all you have to do is add up these two family of inequalities and you get that F plus G minus PKF plus PKG in a product with V minus PKF plus PKG is less or equal than 0 for all V in K. This characterizes the minimizer. So I have that the projection of F plus G has to be whatever is there, which is PKF plus PKG. Therefore, we've proven that PK is a linear map. So when K happens to be a subspace, the projection, which of course in particular is convex, the projection onto that subspace is linear. And that concludes the proof of our first theorem. So we have existence, uniqueness of projection onto convex subsets, and when these convex subsets happen to be subspaces, then the projection is also linear.